The first two slides I'm going to have are going to give you sort of the background of the project. So maybe don't worry if you don't know all the definitions. I'll sort of start on sort of slide, I guess it's going to be 4 by the count, with some definitions and some background. So if you don't know all the definitions right away, sort of don't worry about it. So all of this is joint work with Ian Putnam and Karen Strong. I'll mention the reference, the archive reference later. Okay, so this all stems sort of from a general C-star algebra question. I'm going to be a little bit vague about it, but given a C-star algebra, we can ask whether there exists maybe twisted, maybe not twisted groupoid that realizes that C-star algebra. I'm going to refer to this as a groupoid model for the C-star algebra. So C-star of the groupoid is isomorphic to A. Now, why am I being a bit vague? It's because I don't interpret this question really as a sort of yes-no question. I mean, the no part I interpret as no, but the yes part I interpret as we should be looking for a variety of groupoid models for a given C-star algebra if we can. And one particular groupoid model might be well suited for one type of problem and a different one for a different one. In particular, if we had a twisted groupoid model, we might want to say, do we really have to twist, right? Can we realize this without a twist? And if I had a groupoid model with some, if you're me, anything but a tau is a complicated Haar system. So you might want to say, can we get an tau groupoid that realizes it? Can we make it principal? These are all sort of subparts of this question that is the overarching sort of yes-no question. Okay, so there's been a fair amount of work on this in general and recently, so I just wanted to sort of list out a few names people working on this type of problem and related problems, like taking a groupoid and making maybe an easier groupoid to handle in this regard. That's a lot of names, so I just want to sort of point to one paper by Xin Li, who just put this paper on the archive, and you can look at the references of that paper and the introduction of it. One thing that's important that I want to mention is this classifiable C-star algebra sort of makes this problem a little bit more tractable of realizing a groupoid model, right? Because we can take the Elliott invariant and say, I've got to get a groupoid that's classifiable to hit that Elliott invariant. So that sort of simplifies the isomorphism part of that. All right, so what's the question we're interested in? Well, the question we're interested in, there's really two. So one is, what is the range of the Elliott invariant for cross products by minimal homeomorphisms? So to put this in context with the previous slide, the cross product C-star algebra in this case is coming from the orbit relation. So it's a super nice groupoid C-star algebra. And why we're only trying to realize the Elliott invariant is because we'd also like that minimal dynamical system to fit within classification. And for the reasons I described, that's enough to get our groupoid model of the algebra. Now, the second question, which I'm not really going to talk about question 2, even though the results are better for 2 than they are for 1. But I do want to mention that you can also make these dynamically relevant C-star algebras by doing Ian Putnam's sort of orbit breaking construction. And that's really necessary if we're trying to exhaust the Elliott invariant. So all these algebras are going to be stably finite. And there's going to be some stably finite C-star algebras that we won't be able to realize with minimal homeomorphisms. So I just wanted to mention those things. And since I'm me, I just say the Elliott invariant is roughly speaking K-theory and traces. And in this talk, our goal is going to be quite modest. We're really going to be thinking about K-theory. And I'm even worse, I'm going to just think about K-theory as an abstract abelian group. So we're not even really concerned about the order when we're dealing with these things in the talk. There are better results in the paper. The paper's right here. Like I mentioned, I was going to put it up there. So it's on the archive. Everything's with Ian and Karen. And the other thing I wanted to mention is some of it relies on some previous stuff, but this paper, if you want to see these results that I'm talking about now, you can look there. Okay, so let's get back to the beginning. So I'm assuming that most people are familiar with this, but a minimal homeomorphism means that every orbit is dense. And the reason why we care about it as C-star algebraists is that it is equivalent to the cross product algebra being simple. So if we're thinking about classification, this is why we're putting that assumption in there. Now, I try to say this in most of my talks, it is, you know, an underrated or possibly underappreciated fact that this is the case. You know, we take this for granted because it was established long ago, but this connection between dynamics and C-star algebras and the fact that minimality, which is a fundamentally important dynamical condition, is equivalent to simplicity of this algebra, which is another fundamentally important thing, right, can't be, you know, overstated. Okay. Now, this C-star algebra also has, you know, a bunch of other nice properties. These aren't coming because it's minimal. These are just coming from other aspects. So for example, unitality is coming because we're dealing with a compact metric space. So compactness is giving us that. But, you know, the summary of this one slide is these are nice C-star algebras that are tractable. Okay. So what's our goal? Our goal, like I said, is we're going to take the viewpoint that we're just trying to make the correct K-theories, right, as abstract abelian groups. So you give me your favorite K-theories. What do I want to do? I want to make cross products, minimal cross products that realize those K-theory groups, right? Realize G0 and G1. So this is the goal of the talk. And if it was a yes/no question, we would be done because the answer is there are obstructions. We can't do this. So it's over. But we're going to sort of plow on and try and sort of study this in a little bit more depth. So the obstruction, the most obvious one is that K1 is not going to be the trivial group. You can see this a few different ways. On the next slide, maybe I'll describe how you see that this is non-trivial. So what are we getting? We're getting that this algebra is never AF, this algebra is never the Jiangsu algebra, etc. I do want to mention here, this is where the orbit breaking comes in, right? The simple AF algebras, we're going to use orbit breaking on Cantor minimal systems. For the Jiangsu algebra, there's a construction of this as an orbit breaking subalgebra that's in one of our papers. So this is where we need that flexibility. All right, so we're going to plow on. We're going to say there's some obstructions, but we're going to still try to address this question sort of modulo these obstructions. So how do we deal with this? Well, the Pimsner-Voiculescu sequence tells us how to compute the K-theory of the cross product in terms of the inputs, right? So we're trying right here to get a particular group and right here to get a particular group. So what do we have control over? Well, we have control or want to get control over the K-theory of the space. For unknown reasons, still can't get over calling this just the K-theory of the commutative C-star algebra. This is because I was brought up on index theory and I can't stop. So I have to write it like this, but you can write it like this and everything's fine. Okay, so these are the things we want to control if we're trying to get the prescribed K-theory of the cross product. Okay, so at this point, we, you know, organize a Zoom meeting with our favorite dynamical systems person over a beer or something like this and say, you know, give me a bunch of minimal dynamical systems. I'm going to play with them and I'm going to try and, you know, make the required groups. So we're faced with a purely dynamical question. If you give me a metric space that's compact, does it admit a minimal homeomorphism? And this is a, you know, purely dynamical question that motivated a lot of study in just dynamics. So your friend there would be like, okay, here's a bunch of positive results to get you happy, right? So positive results mean that it admits a minimal homeomorphism. So we have the Cantor set. I just mentioned odometer actions, but there's a lot more minimal actions on the Cantor set. It's a beautiful theory. We have the circle with irrational rotation. And we have odd spheres as another example that's going to admit a minimal homeomorphism. But already you should be like slightly worried, right? Why didn't Robin say all spheres? You know, that would be what you would want, right? That tons of these spaces are going to admit minimal homeomorphisms. Now, before we get totally on the negative side of things, let's look at one more beautiful positive theorem. This is a really stunning result from the late 70s. That if you have a manifold emitting a free S1 action, then it's going to emit a minimal homeomorphism. It's actually going to emit a diffeomorphism, but I'm sort of trying to avoid, you know, what category we're working in and just deal with the topological category. So that's good news. Now some of the bad news. The first bad news is if I have a compact manifold with boundary, non-empty boundary, then it can't admit a minimal homeomorphism, right? And the proof's not hard, right? Just imagine the unit interval, right? Those endpoints, where can they go? Can their orbit be dense? Not so much, right? They've got to go either back and forth or stay the same. And so we see that this is an obstruction. Having a boundary is an obstruction to admitting a minimal homeomorphism. And it's worse. So Fuller in the 50s proves that a finite CW complex with non-zero Euler characteristic is not going to admit a minimal homeomorphism. So here I probably should say that Y has to have infinitely many points, but you know that's a standing sort of assumption throughout the talk. Okay, so that's really bad news. So for example, if I look at one of my favorite spaces, S2, it certainly can't have a minimal homeomorphism because its Euler characteristic is 2. You could also prove it using more directly, but that's sort of illustrating the power of this obstruction. Okay, so now we have to sort of reframe the debate. The issue is that we don't have the variety of spaces that we want that admit minimal homeomorphisms. So we change the goal and we say, I don't care if they're finite CW complexes. I don't care if they're manifolds. Because of Fuller's result, I have to go outside of that world to deal with this problem. So I'm going to ask if you have, I'm going to move to finitely generated groups to make it a little easier. But if I have finitely generated abelian groups, can I find a space that has the right K-theory? Right, K-theory means exactly these two equations, but it needs to, in addition, admit a minimal homeomorphism. Now, here, this copy of the integer z here, this is coming from the fact that it's compact, and we always have that copy sitting in there. So we don't get to specify that, right? If you like reduced K-theory, I'm saying we want to try and specify the reduced K-theory of the space X. And this is the question that we have, and this is the question that we answered positively in the print I alluded to on a bit earlier. Okay, so we want to, sort of outline how we're going to make this space. So we're going to start with what you might think is the easiest case in some sense. I'm going to describe why it's not the easiest case, but why not start, with the beginning? The beginning is these groups are trivial groups, right? So we're looking at a space which only has K0 isomorphic to the integers, and K1 is going to be the trivial group. So first of all, why is this not, the easiest case? Well, the Euler characteristic of this space is going to be 1. So in particular, it's going to be non-zero. So we definitely can't do this with a finite CW complex, right? Our space has to go outside of that class of nice spaces. Okay, so we refer to these spaces as point-like spaces. So to be sort of really precise, these are points-like spaces in terms of K-theory, right? They have the same K-theory as a point. In terms of like homotopy theory, if you like that, they're not going to be point-like. They're going to have some non-trivial higher homotopy groups if people are keeping score. But nevertheless, we're concerned with K-theory, so we're going to think of them as point-like spaces. And so this result we have is this is in the previous work, is that we indeed have such a space. So we have a space that has the K-theory of a point and admits a minimal homeomorphism. Now, I'm not going to talk too much about this construction. It's sort of, one, because I don't have time, but also it's sort of good to not talk about it because we're using it in this particular talk like a black box. So we construct this in a very explicit way. It's involved, but explicit, from a minimal diffeomorphism, on an odd sphere. But if you came along with a different construction of the same type of space, everything I say is going to still be true for it, right? So if you go along, you make a different space, everything going forward will work. Okay, so this, just so we're all on the same page, is the affirmative answer to this very specific case where the groups that we wanted to specify were trivial. All right, so how do we move forward towards more general K-theory and more general spaces? So we're going to use a beautiful result of Glasner and Weiss. This is also from the late 70s. And I haven't sort of completed the statement yet. I just want to do the setup so we're all there with it. and sort of justify why you might believe we could get something like this. So we take one space that's admitting a minimal homeomorphism, that's X, and I'm calling it phi, even though it doesn't really play a role in what's going to happen next. And then we take another space Y and we look at the Cartesian product. And what we really want the conclusion of this theorem to be is that W admits a minimal homeomorphism. That's the goal. Now, why is this somewhat plausible? Let's suppose these were both manifolds, right? And let's suppose that in making this minimal homeomorphism on X, what we actually did was show that there was a free action of S1 on it, right? That was this beautiful theorem that I alluded to earlier. Now, that free action would extend to a free action on X cross Y, right? So it would admit a minimal homeomorphism based on that theorem. Now, what is the value in Glasner and Weiss's construction? Because it does a lot more. Well, first of all, this X didn't have to come from a free action of S1, just any minimal homeomorphism. And Y here is not a manifold. It's going to have to satisfy a different condition. And we want to, sort of have that flexibility, and that's going to be important to us. Okay, so the condition on Y, which I don't want you to, really concentrate on, is really a statement about the space being homogeneous in a certain sense. So if you don't want to read this, that's fine. You just think it's got to be homogeneous as a metric space. Okay, this construction is via skew products, which I just wanted to sort of mention. But again, this is going to be used as an existence result. So it is not important for us in this talk how this minimal homeomorphism was made, right? We only care that it exists, just like with the space Z and that zeta map that was minimal on the previous slide. Okay, so why is this a good thing, right? We're going to apply this when the minimal system, this X var phi up here, is actually the one from the previous slide. And why do we want to do that? Well, the K-theory of that space is just like a point. So the K-theory of W, it just sees the K-theory of Y, right? Because we've subbed in something that's point-like here. Now, let's look at an explicit example, right? We started, we can even be more explicit. Let's say M is the two-sphere, or more generally, a connected closed manifold, right? Then that's homogeneous, right? Well, by homogeneous, I mean you take a point on the sphere, another point, and I can move this point to that point, right? We just rotate it over, right? Now this admits a minimal homeomorphism, and like I just said, it has the same K-theory as that inputted manifold. And sort of more importantly, sort of to me psychologically, is the K-theory isomorphism here is really explicit. So there's not anything fancy going on there. So for example, all the K-theory over here is coming from, if it's a two-sphere, the bot generator over here and the trivial bundle. And we're pulling them back to get the isomorphism. Okay. All right. So despite all that, this condition of being homogeneous is restrictive. In particular, it's not going to be satisfied for most finite CW complexes. So as an example, take our two-sphere that we've been talking a lot about and take the wedge with a circle. That's not going to be homogeneous, right? If I take a point on the two-sphere, it's not going to be able to move by homeomorphism to something on that circle that I've wedged it with. Now how we fix that is we have the theory of Hilbert cube manifolds. So the Hilbert cube is this space here. You can think about it a few different ways. You can think about it as just the countable product of the unit interval with itself, countable times. And that with the product topology. I like thinking about it as I've written it so that you sort of see that it's a metric space and you see how the decay happens and how each component isn't really being treated the same. And that's because we're using the product topology. Now what this does is it makes the space Y Cartesian product Q homogeneous if it is Y was a finite CW complex. So in our example, two-sphere, wedge, a circle, what was the problem? The neighborhood here was one-dimensional. The neighborhood here was like a little two-dimensional thing. But now we've crossed with this whole Hilbert cube, so that dimension conflict is gone, right? I'm not doing the proof, of course. I'm just giving you this sort of intuition as to why we should now be able to possibly move that point to that point and show this is homogeneous. And now the last ingredient is a standard result from algebraic topology, which says that we can realize this using a finite CW complex, so any K-theory groups. All right, so we're running out of time, but let's state that theorem. So we've got finitely generated groups, and we make a space that has the required K-theories and has a minimal homeomorphism. So what was the space? It was built from those pieces on the previous slides. So I'm going to just get all of it out. So Y is the finite CW complex that realizes those K-theory groups. Q is the Hilbert cube. It has trivial K-theory, like a point. And Z was our space. And now we apply Glasner and Weiss's result to this space here to get the minimal homeomorphism on it. All right, so what's happening at the cross product level? Well, at the cross product level, what do we have? We have that this theorem, which is somewhat unsatisfying. So we have a single abelian group entered that's finitely generated, and we have the cross product in both degree 0 and degree 1 has that as its K-theory. So that's somewhat unsatisfactory because we really would like to get, you know, all the possible K-theories. That's what we're working on right now. That's getting written up. Again, in the finitely generated case only. And why this is happening is it's because of what we had in the Pimsner-Wojciechowski sequence. What have we done? We have gained control of the K-theory of the space, but what we don't have yet is control on the induced map. So what we have in these cases is that the induced map we get from our construction is always the identity. And that's what's putting this restriction on the K-theory groups that we're getting here for the cross product. So as I sort of mentioned in passing, we're working on studying and writing up constructions where we don't get the identity as that map on K-theory. And what that'll eventually let us do is get abstract K-theory groups that we want in more generality. I can state the precise result, but because of time, I think I'll end there, and thank you for your attention.